Hello once again, everyone. Mrs. Hanson here, continuing our hard work in Chapter 2 of our lessons. We're up to page 10 of our notes, looking at Section 4 today, looking at the periodic table. And if you recall, the very first page of your printed guided lecture gave you a copy of the periodic table. It would be vital to have that out and just kind of help look through it and look at its organization. So we understand that in the periodic table, we have rows and we have columns. A row in the periodic table is what is referred to as a period. We notice that there are 7 periods on the periodic table, and that if we have a column in the periodic table, a column is referred to as a group. And you'll notice that there are 8 tall columns we will learn are called group A elements, and there are 8 group B elements, where those shorties in the middle. So just kind of clarifying, when we look at our periodic table, we know that going across, reading left to right, represents rows, and those rows are called periods. We see that there are indeed 7 periods on the periodic table. Row 1 is known as period 1, hydrogen, helium. Row 2, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Row 2 is known as period 2. Period 3 contains sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. Finally, in row 4, we hit the first of these transition metals, the short columns, known as the group Bs. The tall group A's are called the representative elements. The shorter ones in the middle are known as the transition metals. And we'll practice those words in our notes, but we're just kind of helping ourselves see periods go across. Columns go down. Column number 1 is called group 1A. It represents its valence electrons. Group 1A contains hydrogen, lithium, sodium, potassium, rubidium, cesium. Group 2A, beryllium, magnesium, calcium, as we read down a column. The next tall column over here is boron's family, group 3A. Boron, aluminum, gallium, indium, thallium. Group 4A, carbon, silicon, germanium, tin, and so forth. Friends, do you notice that on the periodic table you printed, the group A's and the group B's are not denoted? All you see is a numbering system 1 to 18. 1 to 18 tells us there are 18 columns on the periodic table, and you can see those are represented in our text periodic table. Here's column 1, column 2, column 3, 4, and see how we just continue going until we get back to column 18. However, we understand in a moment when we take notes into our chapter, I'm just kind of previewing, that the tall columns that are on the outside edges are known as the group A elements. We will refer to these as the group A representative elements. There are 8 tall columns. We'll also see that there are group B, and we'll write this in our notes, but we're just previewing. There are, and you can see 8 families of group B. Notice that the 8th family here has 3 columns that are part of the family called group 8B. Iron, cobalt, and nickel are all in the group 8B. 18 columns divided into families of group A, representative, and group B, transitions. The main group elements, main group, are called representative elements. The main group are called representative elements. These are the tall columns on the right side and left side of the periodic table. They are numbered as group A elements, numbered 1A to 8A. Group 1A, hydrogen's family, going down the column. Group 2A, beryllium's family, going down the entire column. Group 3A, boron's family. Group 4A is carbon's family. Group 5A is nitrogen's family. Perhaps you'd like to write that on your periodic table just to help you begin memorizing the locations of the Group A elements. Remember, you're only going to be provided a clean copy of the periodic table for quizzing and testing, but if you make notes on this table to study by, I find that very, very smart. The Group B elements are called the transition metals. There are 10 short columns, but they are numbered 1 through 8. Let's emphasize that again. The Group B's have 10 short columns. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 short columns. However, notice how they are numbered into Group B categories. Scandium's family, the first of the short columns, is actually starting with a 3B, and that's because of the number of valence electrons, those electrons in the outermost shell. Then we see titanium's family. Titanium's family is 4B. Vanadium's family, Group 5B. Chromium's family is Group 6B. Manganese family, Group 7B. There are 3 columns grouped together, irons, cobalts, and nickels, all given the Group 8B. Copper is in 1B, zinc is in 2B, going down the columns. Perhaps you'd like to write that on the periodic table I gave you to help you work to memorize. Those transition elements are known as the short columns, Group 1B to 8B, but remember it actually starts with 3, then 4, then 5. Once you get to 8, then it goes back to 1 and 2B. The inner transition metals are located in the bottom 2 rows, and they are known as the lanthanide and actinide series. They are not assigned group numbers, but they are assigned period numbers. The bottom 2 rows are known as the lanthanide and actinide series. It's simply because they start at number 57, here's 58, 59, 60. So think of this little column as saying, go down here and finish the row. When you're done, you come back and start up 71, 72, 73, and so forth. The lanthanide series starts at number 57, lanthanum. Period 7 has the actinide series, and again it comes from the first element in the row, number 89. When you hit 89, you go down and finish this row, hitting 103 to come back to the main group. The lanthanide and actinide series are assigned period 6 and period 7 respectively, but remember they have no group numbers assigned to them. All 14 of these columns here fit inside of that little space. Let me kind of clean this up a little bit. All 14 columns fit inside of this space. So really it's just a way of saving space when we print periodic tables. Imagine taking your scissors and cutting this periodic table where I've drawn a line, shoving this part down, and you take these 2 rows and you insert them right here. That's going to make a really wide periodic table. So just to make it a little friendlier, we remove those 2 rows, place them down below the periodic table, and in our mind we have to think, okay, when I get to 57, I'm imagining that all of these elements in that particular row are fitting in that tiny little space right there. When I get to number 89, all of these elements are really sitting between those 2 AC and RF rutherfordium. It's extending the row. Just to help it not be so wide, we take those 2 rows out and place them down below. We see that there are 3 main areas on the periodic table. The tall columns that are on the outside edges, called representative elements, group 1A to 8A. The shorties in the middle, those are known as transition metals. Transition elements have 10 short columns, but they still only have 8 group B columns. They are categorized by group B denotation. And the inner transition elements are consisting of period 6 and 7 with no group numbers assigned. They're known as the lanthanide and actinide series. Let's try some. Let's give it a try. We're working on an example where we give the period and group number for each element. The first one is aluminum. Aluminum has an elemental symbol Al. And while we're looking, we'll look for the second one, manganese. Manganese has the elemental symbol Mn. Go to your periodic table and see if you can locate the element aluminum and the element manganese. Well, the first aluminum I recognize as being here on the periodic table. To locate its group number, we look up at the top of the column. It is located with group 3A. To find its period number, we count how many rows down it is, and it is located in period 3. So with manganese, group 3A, period 3. The second one we had to write for was manganese. When you located manganese, where did you find it on the periodic table? Manganese is located right here. It's number 25. To locate its group number, you look up. It's at 7B. 7B is its group number, and look what row it's located in for the period. Group 7B, period 4. It's a shorty transition element. Finding the row in the column being the group number, and the row telling us the period. Easy enough. It's like giving an address for every element. Those characteristic qualities that describe metals and nonmetals and metalloids are broken down into similar properties based on the number of valence electrons, those electrons in the outermost energy level. For example, group 1A are known as the alkali metals, alkali. Group 2A has a special name for their family as well. They're called the alkaline earth elements. Group 1A are called the alkali metals. Group 1A consists of those metals, lithium, sodium, potassium, rubidium, cesium, and the very rare element called francium. Notice I am not including hydrogen in the elements for metals. We will learn that hydrogen, even though it's to the left of the periodic table, it is not a metal. It is a non-metal through and through. So hydrogen, you're a non-metal, and therefore you are not included in the family of alkali metals. The alkali metals are in group 1A, but the metals start with lithium. Hydrogen is a non-metal. It's placed in group 1A because it does have one valence electron. It has only one electron. So therefore it has similar properties, but it is not a metal. So group 1A, the lithium, sodium, potassium, rubidium, cesium, francium, those are all known as the alkali metals. In group 2A, this is the family that contains beryllium, magnesium, calcium, strontium, barium, and radium. Those are known as the alkali earth elements. The qualities or properties that both of these groups have in common, they are very soft and shiny metals. When they are not oxidized or tarnished, they're very shiny. They have very low melting points. They're very good conductors of heat and electricity. They react with water to form basic solutions. Basic solutions are the opposite of acidic solutions. Acids and bases are opposites. We also have common names for other groups, such as group 7A. They are known as the halogens. The halogens are fluorine. Underneath fluorine is chlorine. Then we see bromine. We have iodine and astatine. The halogens consist of those particular elements, group 7A. Now, what they have in common is that they exist in elemental form as diatomic molecules. We'll learn that there's actually 7 elements that exist as diatomic molecules instead of atoms. Now, what that means, for example, in nature, I never find just a single fluorine atom. It's always joined to either another fluorine, giving me an F2 molecule, or fluorine can be bonded to a different atom, but it has to be bonded to something else and not left as an individual atom. In nature, I never find just a single atom of chlorine. The elemental form of chlorine is a diatomic molecule, Cl2. Iodine, bromine, same story. Their elemental form is as a diatomic molecule. So if it's an element, they'll be joined to a like atom. Now that also includes, it could be a compound, fluorine, chlorine, bromine, iodine. They can be in a compound joined to a different atom. We're just saying because they're kind of reactive, we need to make sure that they're bonded to something else. So qualities here of the halogens say they exist as diatomic molecules and they're very reactive. Group 7A are called halogens. Now, in the note pack, it looks like I wrote properties 1, 2, 3, but there's really only 1, 2. Do me a favor, and with property 3, just draw a line. I think I had said noble gases. Those are the 2 properties there. So there are 2 to write for the noble gases, and 3 were given for this, but we're only going to write 2 for the halogens. So for number 3, just draw a line. In group 8A, it says they're called the noble gases. Sometimes you hear them called the inert gases. That's because their outer shell is already full with an octet. They're the envy of every other molecule or atom on the periodic table. So they're very stable. They rarely combine with any other elements, the noble or inert gases, group 8A. So we've just talked about different properties and names of special families on the periodic table. Let's practice a little bit using our periodic table and try to identify the elements that fit the following descriptions. So with your periodic table, please pause the video, work through these 6 example problems, place an answer on your paper, and when ready, come back to the video and we'll check our work together. I stress every time, don't cheat yourself of the practice. Pause, put your answer down, and come back. All right, welcome back. So with our periodic table, an alkali metal in period 4. So we have to remember the term alkali metal means group 1A. So an alkali metal in period 4 brings us to, make it yellow, period 4, group 1A, that's potassium. Potassium with an elemental symbol K. The letter B gave us a second row element in group 7A. When you say second row element, it's describing for you period 2. Group 7A, period 2. So as I highlight group 7A, period 2, that intersects at the element fluorine. The element that is in the second row, group 7A, is the element fluorine with its symbol F. Letter C. a noble gas in the third period. So when I'm looking for the noble gas, I have to remember that's the description to the column 8A. Helium, neon, argon, krypton, xenon, and radon are all examples of noble gases. And if I want the one in the third period, it means the third row down, that's the element argon. So letter C, you wrote argon with its elemental symbol Ar. Letter D, this one reads a main group element in period 5, group 2A. Period 5, group 2A, well that's strontium. Letter D is the element strontium with the symbol Sr. Period 5, group 2A. Letter E, a transition metal. Those are the shorties, right? And group 12, period 4. So now all of a sudden, with this particular example, we're seeing the numbering system 1 through 12. So the column marked the 12th column out of 18 is what it's referring to. So that looks like zinc's column. And it also says in period 4, so we want to go to the 4th row down. Intersect the group at number 12, intersect the period at 4, and you get the element zinc. So in letter E, we wrote the elemental name zinc, Zn as its symbol. And there was one more, letter F, a transition metal in group 5, period 5. So with this example, notice that group 5, and in period 5, gives us niobium, Nb, niobium. Some of those are just fun to say, aren't they? So we wrote down those answers you've had a chance to check. Now we have an element, kind of an unusual natural element that gives us the heart of organic chemistry. It's called carbon. Carbon has an ability to join with itself and with other elements to give just a highly versatile way of creating other compounds that are very stable and really give us the basis of life. It's very versatile, more so than any other element on the periodic table. Elemental forms of carbon include 3 different allotropes. They are called diamond, graphite, and Buckminster fullerene. Based on those structural arrangements, notice the carbon in diamond. When you look at the molecular structure here of diamond, you'll notice that it has kind of an arrangement in a highly ordered fashion. Graphite gives us sheets. And Buckminster fullerene kind of looks like a soccer ball. You have these repeating patterns of 60 carbons joined in a sphere resembling soccer ball. 3 naturally occurring allotropes, different forms of carbon-to-carbon bonds that lie the groundwork for all kinds of other types of molecules, known as naturally existing molecules. Organic chemistry lies in this field. All right, we've spent time looking at the periodic table and kind of just a general organization of the elements. Let's dive into really what we find interesting as a chemist is the electronic structure of atoms. So just reminding ourselves, we know that protons and neutrons live in the nucleus, and we have the positive protons and the neutral neutrons, and we can just kind of think of those as particles. And if I don't draw a charge in there, you know I'm referring to a neutral neutron. And we've talked about the electrons residing in outside of the nucleus. We've never really discussed yet how they're organized. So that's where we're going to pick up with this story, is the organization of electrons outside of the nucleus. So an electron is confined to a very specific region around the nucleus, and we refer to those very specific regions as energy levels. So they have a very particular energy that they're allowed to reside in. These regions occupied by electrons are called principal energy levels. Sometimes you'll hear those called shells. And they're abbreviated with the letter N. N stands for the principal energy level. These shells are numbered to let you know the energy contained in each orbital. So if I have a nucleus with positive protons and these neutral neutrons, and I draw a first energy level, or a shell, this is where N equals 1. N equals 1 is of lowest energy because it's closest to the nucleus. We will learn that at maximum there's 2 electrons in the first energy level. There is a second energy level. We draw that second ring. We call that N equal 2. The shell, or the second energy level, is a little further away from the nucleus than the first energy level. We will learn that at most there are up to 8 electrons that can occupy the second energy level. 1, 2, 3, 4, 5, 6, 7, 8 little dots in that ring. At most, we have 2 electrons in the first, 8 more in the second. If I were to draw a third ring around that nucleus, we would say that's N equal 3. The energy of the third is a bit higher because it's farther away from the energy level. N equal 1 is the lowest energy possible. It's the closest to the nucleus. And as I add rings farther and farther away from the nucleus, those have higher energy than the ones that are closer to the nucleus. So if N is a high number, it represents that its distance is further away, and it represents that it's a higher energy than a shell that is closer. Let me kind of go back to the periodic table and repeat what I've just said to emphasize these shells. So I'm going to go back here and make a few notes. A moment ago, I said in the first energy level, N equal 1, that's the first ring around the nucleus, right? In maximum, we can see that there are 2 electrons in the first energy level, and then it's full. Well, why is it 2? In the first energy level, it represents the first period on the periodic table. How many elements do you see in the first period? Well, I see 2. There's hydrogen, helium. Hydrogen has 1 electron. Its atomic number is 1, telling me that there's 1 positive proton. By definition, the atomic number tells me the number of protons. And because atoms are neutral, it also tells me the number of electrons. Hydrogen would be a single proton in the nucleus with 1 electron outside. That's a kind of its rough model, 1 electron. There is a second element in that first row as well. It's helium. Helium, we discovered, has 2 positive protons in the nucleus, 2 neutrons, giving me a mass number of 4. And it would have 2 electrons because 2 protons must match the number of electrons. So at most, there's 2 electrons in the second energy level. Then it's full. When it's full, and I go down to the next row, that next row is lithium's row, period 2. When I go down a row, I have to add a next shell. Adding a next shell says N equals 2, a second ring around the energy, right? So N equal 2. How many elements do you see in row 2? Well, I see 1, 2, 3, 4, 5, 6, 7, 8. There are 8 elements. Each one of those is adding 1 more electron to its electron configuration, the arrangement of those electrons. And I know it's adding 1 more electron because the atomic number is increasing by 1 as we move left to right. So when I add a next electron, that's lithium. Add a next electron, that's beryllium. Add a next electron for boron. Add a next electron for carbon. one more for nitrogen, one more for oxygen, one more for fluorine, one more for neon. And by the time we've added the electron arrangement for row 2, we have said that there's 8 electrons maximum in that second energy level. Then the row is full. We've reached the end of the row. Once we hit neon, that shell is closed down as full. A noble gas configuration has been achieved. Well, I go down to the next row. That's period 3. Period 3 belongs to sodium. Where do I put its next electron? Well, you're right. I've got to add a next energy level around the nucleus. So I added a second ring for row 2. I will add a third ring for row 3. And so forth. So each time I add a row, remember I said there's only 8 electrons at this point because there's 8 elements. So now all of a sudden I'm getting an idea of where we're heading. The arrangement of electrons outside of the nucleus has a very specific pattern, and it all falls in the secret of saying it has to do with where the element falls on the periodic table. N are the shells, but really I know those shells by the period number it resides in. How many shells or energy levels is determined by the element's period number. How many electrons can go into that subshell is determined by what group number it lies in. Let's keep talking. We know that shells with larger numbers, the N, are farther away from the nucleus and can hold more and more electrons as we add them. The maximum number of electrons can be determined in each shell by given a quick little formula, and that formula is 2n squared, where n is representing the shell for the number. Now let's practice that, the distribution of electrons. And I'm going to start down at the bottom of this at shell number 1. When I look at shell number 1, n equals 1, and we're going to use our formula 2n squared. What's 2 times 1 squared? Well, 1 squared is 1. 2 times 1 gives me 2. At most, our first energy level can hold 2 electrons. We said that. That's hydrogen, helium. What if n equals 2? So this means 2 times 2 squared. 2 squared is 4. 2 times 4 gives me 8 maximum electrons. Well, we knew that. Period 2 has 8 elements: lithium, beryllium, boron, all through neon. If n equals 3, 2 times 3 squared can be used to calculate the maximum number of electrons that can be found in each shell, each principal energy level. 3 squared is 9, so 2 times 9 gives me 18. In the fourth energy level, that's the fourth ring around the periodic table, we notice that now we're finally getting to some transition elements and so forth. 2 times 4 squared. Well, 4 squared, 4 times 4 is 16. So 2 times 16 is 32. There's 32 electrons maximum that fills the fourth energy level. So that little trick helps us determine how many electrons in each of the principal energy levels. The n equal 1, n equal 2. Those are the rings around the nucleus called energy levels. These shells, or principal energy levels, are also divided into what we refer to as subshells. These are identified by 4 letters, and those letters represent shapes of the orbitals. S represents the spherical shaped. You'll see those look like spheres on an XYZ axis. P stands for principal. And we'll notice that there will be 3 different spatial orientations on an XY axis. P's look like hourglasses, or kind of the figure 8 or a dumbbell. Here is a P sub Y. Looks like a little hourglass on the Y-axis. Here is a P sub X. Looks like an hourglass. And on the Z-axis, I should have maybe drew those separately. Here is a P sub X, P sub Y, and a P sub Z. All I'm giving you is spatial orientation of a P axis. So what we look at is with an S-shaped cloud, spherical, P-shaped clouds look like little hourglasses. These little things that I've been drawing are referred to as orbitals. That's the very specific location within the shell we have subshells. And the orbital is the region of space where the probability of finding an electron is quite high. In other words, mathematically speaking, I'm pretty sure an electron is within this spatial arrangement at any one given point in time, because electrons move extremely fast, so fast that they are more considered waves than matter. Each orbital can hold at maximum 2 electrons, and each must have opposite spin. So with the subshell, an S-shaped orbital has one shape. An S shape is spherical. I'm going to add another column here, and I'm going to say number of electrons, and I'll maybe even put maximum number of electrons. In an S-shaped orbital, which is just spherically shaped, there is one shape to that on an XYZ axis. Each orbital can hold 2 electrons, each with opposite spin, so that's 2 electrons max. A P-shaped orbital, that's what I was drawing as these hourglasses, has 3 different shapes. I call them a PX, a PY, a PZ, based on which axes of a 3-dimensional XYZ axis it was orientating itself around. So with 3 orbitals, each of these orbitals can hold 2 electrons. So if there's 3 orbitals, each holding 2, there's a maximum of 6 electrons in the P subshell. The D shells have 5 spatial orientations. These actually look like little 4-leaf clovers on an XYZ axis. You can see I'm a wonderful drawer. And you just kind of keep twisting those around the XYZ into 5 different locations. So 5 different orbitals, arrangements of electrons. Each of the 5 can hold up to 2 electrons, so now you're looking at a total of 10 to fill the D sublevel. And really large atoms have an F-shaped orbital, 7 different spatial orientations. That's another way of saying number of orbitals are spatial orientations. How many different ways can I arrange those electrons? Each of those arrangements holds up to 2 electrons, so that's a total of 14 to fill the F sublevel. So let's put that together in a grid. If n equals 1, I have 1 orbital. It's an S-shaped cloud. The number in this sublevel would be 2 electrons, because each electrons in each subshell, maximum number of electrons. Well, the S orbital can hold 2 electrons, so at most the first energy level holds 2 electrons. If n equals 2, we have 2 different types of orbitals. We have an S-shaped cloud and a P-shaped cloud. S's can hold 2 electrons. The P-shaped clouds, which have 3 different spatial orientations, can hold up to 6 electrons. Remember, we had a PX, a PY, a PZ, and that gives me a total of 8 electrons in the second energy level. 2 in the S, 6 more in the P. In our third energy level, we have 3 different types of orbitals: an S-shaped orbital, a P-shaped orbital, and a D-shaped orbital. Remember that S's can hold at maximum 2 electrons. At maximum, P's hold up to 6 electrons. So the S holds 2 electrons, the P holds up to 6 more, and the D's, because they have 5 spatial orientations, they can hold up to 10 electrons. 2 plus 6 plus 10 gives me 18 electrons. And if n equals 4, we have an S-shaped cloud, a P-shaped cloud, a D-shaped cloud, and an F-shaped cloud. The S's hold up to 2 electrons. The P's can hold up to 6 more. The D's can hold up to 10. And the F's hold up to 14. That's where we found 32 is our maximum number of electrons. This column is a moment ago where we gave this formula, 2n squared. If n equals 1, 2 times 1 squared is 2 electrons. If n equals 2, 2 squared is 4. 4 times 2 gives us 8 electrons. If n equals 3, 2 times 3 squared, 3 squared is 9. 9 times 2 is 18 electrons. And lastly, if n equals 4, that's the 4th period. Potassium's row is the 4th period. 4 squared is 16. Doubled is 32 electrons. The total number of electrons in an energy level, which is the period, can be given by this formula. This column lets us know specifically where those 32 electrons are located, what subshells. So I can see what subshells are S, P, D, and F orbitals, standing for spherical, principal, diffuse, and fundamental. Those letters stand for something. And that's what we filled in there. So we're able to figure out how many different orbitals, how many subshells, and how many electrons we have. The s orbital contains 1 subshell. The second shell contains 2 different orbitals, the s and the p. There are 3 spatial arrangements, 3 different orientations for the p orbitals. In the third energy level, we have an S, a P, and a D-shaped orbital. The S has 1 spatial orientation, the P's have 3 spatial orientations, and the D has 5 different spatial orientations. Each one of those represents the term orbital. If each one of these orbitals can hold up to 2 electrons before they're maximized full, that's where we're getting 10 electrons. Again, fourth energy level has 4 different subshells. We have an S-shaped cloud, a P-shaped cloud, a D-shaped cloud, and an F-shaped cloud. S has 1 spatial orientation. P's have 3 different spatial orientations. D's have 5, and the letter F-shaped clouds have 7 spatial orientations. And that means it can hold up to 14 electrons, giving us the 32 we calculated in that last row. It's a lot to kind of process, and I think just kind of putting it into work will kind of help bring this picture together of the arrangements of electrons. So let's practice. We have a little practice problem to kind of think about shapes and orbitals. I've mentioned that an s orbital has a spherical shape. These orbitals get larger in size as the shell increases. That means it's getting farther and farther away from the nucleus. So if this is the nucleus of an atom, the first S-shaped cloud kind of encompasses that nucleus. The second S-shaped cloud, n equal 2, is bigger, and it completely encompasses what's inside of that is a 1s and the nucleus. Then I start drawing the p clouds. Here's the first p-shaped orbital. Those are the next 2 electrons, bigger than the s shapes it's containing. Here's the next s orbital, 2 more electrons encompassing everything inside of it. Here's the next p-shaped orbital. I just drew in 6 more electrons. So kind of envision with me. Here's the nucleus. The first 2 electrons are making an S-shaped cloud, moving so fast everywhere, they're making a spherical shaped cloud covering, that's n equal 1, 2 electrons in an S-shaped cloud. Then the next 2 electrons also create an S-shaped cloud, but it's bigger, so it's encompassing everything inside of it. So n equals 2, I just drew an S-shaped cloud holding 2 electrons, making it spherical, and it's bigger than the n equal 1, so we don't see it anymore. But in n equal 2, the second energy level, we also have p orbitals. There's 3 of them, px, py, pz. Just again, based on the orientation of what orbital it's encompassing. If it's on the y-axis, if it's on the x-axis, or if it's on the z. So that's what I'm trying to draw next. The next 2 electrons fill a p orbital. Let's say it's filling py. Here's 2 electrons. That p orbital has 2 electrons in it. That's this guy. The next 2 electrons get placed and they fill this orbital. That's 2 more electrons. And 2 more electrons fill in the last orbital, px, py, pz. So you had 3 different orbitals for p, each holding 2 for a total of 6. So the second energy level, with its S-shaped cloud and 3 different P-shaped clouds, giving me a total of 8 more electrons. This, by the way, would represent the element neon. Neon has 10 total electrons because its number is 10. The first 2 electrons went in the first energy level. The next 8 electrons went in the second energy level to give me a total of 10. And so forth. So as we begin increasing size, increasing electrons, we're just looking at the spatial arrangement of these electron clouds. How many electrons are present in each shell, subshell, or orbital? The first reads a 2p orbital. So let's remember what the term orbital means, right, from our previous page. What is an orbital? I'm trying to find the page we defined it. An orbital is a region of space where the probability of finding an electron is high. Each orbital can hold only 2 electrons with opposite spin. The reason I took some time to find that is the following. A 2p orbital. Now, this is telling me that it's the second energy level, and that means that n equals 2. P is telling me the shape of the cloud, if you will, that it's going to be an hourglass shape. But this key term here, an orbital, that's the only word that pertains to this question, because any orbital can only hold 2 electrons, and they'll be opposite spins. If one is spinning clockwise, the other is spinning counterclockwise, again, to reduce repulsive forces of the like charges. So with this question, I want to emphasize the only thing that's important is the term orbital. Any orbital can only hold 2. I don't care what energy level it's in. I don't care the shape of the cloud. Any orbital holds at most 2 electrons. How many electrons can be in the 3D sublevel, the 3D subshell? So that goes back here. In the third energy level, we have a D sublevel. There are 5 orbitals. Each one of these orbitals can hold 2 electrons, but since there's 5 different shapes of the D orbital, a D sublevel can hold up to 10 electrons. So the D has 5 orbitals. Each orbital has 2 electrons. And that means we have a total of 10 electrons in the D sublevel. It does not matter what energy level. No matter what energy level I find D in, it will always have 5 little orbitals, each having 2 inside for a total of 10. Number 3. 3 says the 3D orbital. Well, what's the difference between number 1 and number 3? I gave you a 2p orbital. Here I'm giving you a 3D orbital. At most, any orbital can only hold 2 electrons. It doesn't matter what principal energy level. It doesn't matter the shape of the orbital. Just that any orbital has only 2 electrons inside, each with opposite spin. And the fourth, the third shell. So n equals 3. Think about what that means. The entire third energy level, how many electrons total? We'll have 2 in the S-shaped clouds, 6 more in the P-shaped clouds, and 10 more in the D-shaped clouds to give us a total of 18. That can be solved for quickly. If n equals 3, our formula says to find the total number of electrons for any particular shell, take 2 times n squared. 3 squared is 9. 2 times 9 gives me 18 total electrons. In n equals 3, you will have 2 in the S, 6 more in the P-shaped clouds, and 10 more in the D-shaped clouds. 2 plus 6 plus 10 gives us 18 total electrons in that third energy level, and then it's full. We go down to the next subshell then. We put this together writing electron configurations. When we come back with our lesson, we're going to practice writing electron configurations in section 6.